Okay, today's deep day. We're going deep into what makes classical mechanics work. And in the process of doing that, we're going to just sketch a little bit about how quantum mechanics works and how they compare to each other. So let's get started. The thing that we'll be messing with throughout this course are partial derivatives. I don't think I need to spend much time on this. You guys have all taken what's equivalent to Calculus 3 in this university. And so you probably know that if you have partial derivatives, they're symmetric to the order. But still, you're going to be teaching students, and I'll just run very quickly through the Beaver Lake Boathouse geometry of the partial derivative in just x and y. So let's go ahead and get with that fairly quickly here. But what I'm really interested in having you learn right at the beginning is this scaling that we looked at between the two ellipses and the what I call the zeroth Hamilton and Lagrange equations. And then out of that follows the first, both Lagrange and Hamilton differential equations of mechanics. And in the process of studying that, we're going to see a little bit of how just the fact that the speed of light is constant, really, really constant, all of classical mechanics and quantum mechanics follows from that in a logical way. I'm going to just sketch a little bit of that. That's Unit 8, okay, of this textbook which you haven't received, but you can look it up, and you can also take advantages of this, what I call Chapter 0. We're hoping this will be Chapter 0 for that great big Springer-Verloc encyclopedia, but it's one of those things that could depend on how much space they have. In any case, that's something that I think you'll enjoy that, even if it's not completely explained. Anyway, the contact transformations that happen in classical mechanics. Very often, mechanics books come out, particularly the American ones, in which they talk about the contact transformation. They never explain why the word contact is even in there. That's something that's a geometrical effect. And it's an effect that involves the wave mechanics behind classical mechanics, namely quantum mechanics. So we got a big day today. Let's real quick here go through the Beaver Lake Boathouse, in particular, trying to figure out, if you know where this is in Z, how do I find where this is, where I have to go 2 steps, say this way and this way, or let's try going the other way. And if the boathouse hasn't collapsed from a hurricane or whatever, this thing should be right at the same point that is, and by demanding that, you get the symmetry of the partial derivatives. Okay, that's, I think, is everyone's sort of on that wavelength and have seen this and think. So I can really zip through this without hurting anyone. In any case, if you are having trouble with this, I'll make sure you review it. So there's the going up one way, there's going up the other way, and finally we get something where we meet at the middle there, and we compare them and see what you get when you make that comparison, and that's when you get the result that we're after here, namely symmetry with respect to partial differentiation. So, okay. Now, just remember, and we're going to really remember this as we go through the mechanics today, when I say partial derivative with respect to x, and I'm in a thermodynamics book, some of the older ones particularly, they might write the derivative that way, the way it should be in almost all math texts, but often they'll draw a line here and they'll list all the variables that didn't change. Okay? And for somebody that knows calculus, that's unnecessary. I see these little curly D's, I know right away. That's the variable that's allowed to change, and the others have to stay still. But when you have a whole pile of variables, and we kind of have that in classical mechanics, a little reminder is needed. And then the whole idea of what it means to have a partial derivative that's zero. Okay, notice the thing doesn't depend on that at all. That's what we're going to wrestle with as we go through this. But before we go on, there's a thing called the chain rule. You've all seen this too, right, in the calculus that goes with the discussion of symmetry. Our notation for a time derivative, just to save space, and it's a little unfortunate because sometimes the little dot here gets lost in the pixels, but that's going to be our notation. So dx dt will have a dot on it, dy dt would just be a y with a dot on it. This is what I call shorthand notation. Okay, and it's pretty standard, so we'll make use of it. So, and let's move some of these other guys along here because we're really going to need these other screens here to help us with some of the stuff that's coming in the quantum section here. So, now, I will often have a derivative with some other parameter, in which case a prime might be called, and then I have a prime on each one of those things. So that's a notation that we'll be wrestling with from time to time here. The main thing I want to get to now is on the far screen there, and I'm going to put it on this one too. But before I do that, let's go one more line here. And there's our symmetry relation. Now this is a real shorthand notation. If you're taking a EM course with Jackson, that's pretty much a thing. Just a subscript means a partial derivative. And you're going to see that if you go into relativity, particularly general relativity. That's one of the notations anyway that is used. Okay, now, oh yes, there's one other thing, the standard Gibbs notation. And we're going to be dealing with that next week when we talk about complex variables applied to physics. And this little dot product right here between the differential x and y and the well, del of some function of x and y, which is what we're talking about here. Okay, so this, just to make sure that that's up to date, trying to get everything up to date in Kansas City here. And then this is what we've got to talk about. This is where it all begins, if you're just doing the classical shtick. Lagrangian is an explicit function of velocity. That's sort of a canonical statement. And that's the thing about classical mechanics. You keep hearing about canonical variables. And you have to ask, what does the Pope have to do with all of this? This goes way back into history, where something was canonical, was blessed by the Pope. Well, these are the days when we don't respect, as a society, as much the idea of canonical. In any case, you're going to hear it used in any text that you read, or any paper that you read. It's written by somebody that's about as old as I am, will be using that terminology. Now, what you won't see very often is the guy that we put in between the Lagrangian and the Hamiltonian. So, what we've done when we talked about this was we've got an ellipse for the velocities of the SUV and the Volkswagen, or the Super Ball and the pen that was riding and colliding with it. That was our space, was the two velocities in the problem. And Lagrange, the French approach to mechanics, based on velocity very much. And then on the other side of the gulf between Britain and Ireland is the Hamiltonian. This is the Irish approach to classical mechanics, in which we work with momentum. So the energy being expressed in terms of momentum, this one energy expressed in terms of velocity. Okay, that's all you got in most of the mechanics things. We added this one, and we're going to play with it a little bit, but not so much today. So these two are going to be playing against each other. This was a convenient one for our geometry, because ellipses became circles. That was really all there was to it. Okay, but that's a lot. In any case, here, this matrix that has, and for our uses, is diagonal. But later on, when we talk about angular velocity, it'll be full of numbers on all sides, and it'll be 3 by 3. Okay, so that's coming up, not right away, but not too far from here. Anyway, the same thing's true for the inverse of this matrix, which is what the Irish Hamilton crew would be using. So M inverse is the key quadratic form that describes energy in that way of looking at things. Okay. Now, here's what we try to make the logic of all of this have some bite to it. And this is where you get in trouble in thermodynamics if you don't take advantage of this. So it's worth looking here. Now, if we were going to fuss around with the Lagrangian, we would make a point of saying that the Lagrangian Hamiltonian had no dependence on that weird variable that what do you want to call it, speedinium or speedium? Okay, the thing where you had the square root of the masses times the was ordinary velocity, where you had the half power of the quadratic form times the velocity. Now, as I say, we're not going to go into that one very much, but these two we really need to make clear what we demand from the calculus of this. We want the Lagrangian, and if you're going to do Lagrangian, we want it too. But here, we want the Lagrangian to have no explicit dependence on momentum. And then the Irish said, no, I'm going to work with energies where I have no explicit dependence on velocity. Well, who's right? Well, they're both right. That's what we're going to try to make. So we write the zeroth equations for mechanics as far as the French are concerned, the Lagrange is concerned. The partial derivative of L with respect to P is identically 3 equal signs 0 energy the same way. So that is the starting point for the Lagrange thing. This is the starting point for the Hamiltonian, and that is that the Hamiltonian shall not ever be an explicit function. What's this explicit function? We're going to have to explain that. That's going to take some explaining. But same with energy. We don't want any dependence in the formal sense of the velocity variable. Okay, well, what do you do when something like that is going on? And that's the rest of this right here. And I'll go ahead and put this one up in the same position. Okay? So, by demanding this set of equations here, that is the partial with respect to V, and that's the expression we're going to use for the Lagrangian, and this is its derivative with respect to velocity. Well, what do you have? P here, take the m dot v, okay, when you take the partial derivative with respect to v of this thing, in this vector notation, you get P. And the same thing's true down here in the Hamilton world. When I take the partial with respect to P of this quadratic form, well, I get a linear form, okay, and that happens to be the velocity. So, you could say, well, now I understand all of the calculus dependencies from classical mechanics. Not quite, not quite. Something's weird going on here, because we know darn well that when I change V in something that involves Hamilton's work, or I change P in something that involves Lagrange's work, it's going to change. But we were speaking of some kind of formal thing here, some canonical. Well, we've got to justify that canonical. We've got to have more than just an edict from the Pope, or what they used to be called a papal bull. Okay, we need less bull in the description of this crazy stuff. Okay, so that's what we're after. Now, as we're going to see on page about 28 or so, the non-dependency due to stationary value effects is what is behind this on the classical side. It's called a contact geometry, which we are going to have to look at more closely very shortly here. So let's just remind us what the geometry looks like. When we plotted the quadratic forms, we got ellipses. In the case of the quadratic form that involved the quadratic velocity, that was a velocity space. So these were the variables we were working with. In the background, we noted that this is a p variable, but the explicit dependence is to v. And v happens to be p over m, just as the p's happen to be what you're more used to, m times v. And it's this geometry that is so key to understanding more clearly the dependencies, the crazy sort of dependency behavior that we're messing with right here. So this is the, go ahead and go right to the meat of this with all of the equations that we've so far demanded. We haven't really deduced, but we're making some sort of axiomatic calculus approach here. The first equation of Lagrange is just that p, the actual p vector. And this picture that I'm drawing here is weird, because what I'm doing is I'm drawing the Irish diagram that involves the momentum on top of the French diagram over here that uses velocity. Okay? But that's what we do with quadratic forms. We forget for a moment the physics a little bit and just look at the geometry. So what I'm saying is that this p momentum right here is the gradient of the Lagrangian. There's a Lagrangian right there, and it's a v dependency, so I apply that, and I get a vector. The gradient of the Lagrangian right there is p. Okay, there he is, the gradient, perpendicular. That's a little perpendicular sign, right? And there's p right there. And then there's the flip side of that, which we've been through this already, but it's weird. It's interesting to see it in this diagram. We're going to make a lot of use of this diagram when we come to rotations and things like that. But before that, we will be messing with it. Here, velocity, that's the first equation of Hamilton. The p gradient of the Hamiltonian is going to be the velocity. Okay, whatever the velocity is. Well, there's the p gradient right there, perpendicular, you see, to the tangent. And there it is, when its butt is put on the origin where it belongs. Okay? Is this making sense? All right, this is the key sort of things. Now, how do you scale these? We did a little bit of fooling around with the scaling of quadratic forms. If I talk about a lesser mass, okay, then this guy shrinks. If you recall, the major axis, minor axis, minor radius, which you call B, major radius, call it A, if it's an ellipse, A, B ellipse, okay? Well, they got the square root of the mass in there. This thing has the square root of the inverse in it, this thing right here. Now, it's very finely written, but you recall that. So it might look like this, it might look like this. In all cases, you see, the tangent is going to be perpendicular to the momentum, even if the ellipse of the Lagrange is big. If it's smaller, it still works. This is scaling independent. Okay, just a minor point, but one that's worth keeping ties on. Okay? All right, now, what is it that we're actually looking at if I'm allowed to actually plot the values of, say, the Hamiltonian? That is, think of this as a great big sort of ornate bowl coming out of the screen. There's the lowest point. Here's the point that's right on the board right now, and then above that would be more real estate on a parabola, elliptic paraboloid, right? Is this a pretty clear thing to imagine? That's what I want to imagine. I now want to look at the cross section of that and do this stuff all over again. Okay, that's what we're after here. So I'll leave that picture up, and we'll go and do some other stuff on these two screens. So here we go, introducing Poincare and Lagrangian contact transformation between the two of them. Okay, now this is really squirrely. This beginning thing right here is really squirrely. We have much better derivations of what I'm about to show you here that will come, well, later in this lecture, but particularly in the next one coming, where we actually start to make generalized coordinates work for us. But given this relationship of P is a quadratic form times V, good old momentum equal some mass thing, a matrix, times the velocity vector, here's the inverse. We presume that we don't have any singularities of that thing. If you do, you stop right there and don't do anything. But if you do have a valid quadratic form, that's what it looks like, and the equations that we've been writing so far mirror that, and the same thing for these. So, you might be tempted, as I say, to rewrite the Q forms in a simpler way. Why mess with Q forms? Well, why not let the Hamiltonian here just be, and this is M inverse P, that's V, just like P dot V. Or I could go and take this one right here. M dot V is P, so I could write it V dot P. And this is classical physics here, so these commute. These are both the same numerically. So what I've done is numerically correct. Okay? But functionally, it sucks. Numerically correct, differentially wrong. Okay? So that's what we're going to be arguing about, is the differential behavior of this as well as the numerical values of these functions. Okay? Now, as I point out there, classical physics, you don't care about the order of P and V. If these were operators, it would very much so depend on that, but not here. So what we do is we take sort of the halfway road here. I go and say, I think I'll make this P dot V minus 1/2 V dot P. See how that works. Okay? Well, 1/2 V dot P is L. Okay, if you want to just consider the behavior with respect to V. Oh, you want to play Irish? Okay, you want to get into Hamilton's country? Okay, well, let's do P dot V minus H of P. We can have that as well. That would be the Lagrangian. Okay, now how does that work? How in the world does that work? Okay, now this is one of the most famous equations. This is the doorway to understanding how classical, whatever you want to call this thing, relates to the wave mechanics. And we'll see that several times later. But this is one equation and this is the other, and we're going to, as I say, derive this other ways, but let me point out, if I have a working laser pointer here, and I don't think I do, not for the green, maybe for the purple. Let's see if we've got a purple. Yeah, purple one works good. And there's a lot of fluorescent dye in paper, so it makes it so white. So let me get this thing working. There we go. Right there is the Hamiltonian expressed in terms of Lagrangian. So right there is this equation. Now it looks a little different. I've got P with superscripts and stuff like that. So I've got a P dot V. V is Q dot, and then minus L. Okay? So those are, that right there is the, I call it the Poincare equation. The Poincare is the one that really made a fuss about this. And then the very first equation, gradient of h is equal to velocity, is right here in the notation that we'll be using when we use these kind of weird generalized coordinates that you need to study relativity. Okay? Now that's the second equation right there. We'll get to that later. But for now, we've got the first equation for Lagrange, and this is the first equation for Hamilton. And this is the connection between those two quantities. Now this is the full-blown thing which we're going to work out in a day or so here. But right now we're just messing with the functional dependence of these objects. So, the explicit dependency or non-relations gives the right derivatives. This is a good choice. You can see right away if I take the partial derivative with respect to p of this side right here, and then I do a partial derivative of with respect to p of that thing, I just get a nice v there, okay, v, right? And then minus, I take the partial with that respect to p, that's supposed to be legitimate to do. There's your Hamilton first equation, right there. V equal gradient of h. Same thing here, I go and take the partial derivative of v with respect to this. That's 0 by definition here. And then these work out to that's the first Lagrange equation. I'm sorry, this is the first Hamilton equation, this is the first Lagrange equation. Okay? All right, that's basically what it is that we're playing with in these pictures right here. Okay? That's the first of these equations. So let's, I'm going to bring this screen here. Let's leave the one that has that kind of geometry on it up, and I'll jump ahead here on this screen up there. We don't need the Lagrangian anyway, so I'm going to bring this guy up to where we are. Whoops, I went too fast. Okay, that's what we really want to look at there. That's next. But I'll leave the algebra for the time being on that screen there. And then I just touched something there that made this one move, and I didn't mean to do that. Okay, so there's the basic algebra, and there they are on the wall, as though some deity has written them. And this, just to remind you, the geometry of these things, the tangents, where they are, and all of that. Okay. Now, here's what it looks like. Here's what that thing on the V1 versus V2 or the P1 versus P2 graph of ellipses looks like turned on the side. Okay, so you have to imagine now an ellipse that's edge on here. Okay, we're looking at a particular point on an ellipse. It comes out of the board, goes back in, and goes into the board, and so forth. Okay, so there's your parabola part of the elliptic paraboloid. Okay. And here's the one that Hamilton's offering you. This is Lagrange over in Paris. And here we are in Dublin with Mr. Hamilton. That's what he's going to plot as his function of, now he works with momentum, he doesn't work with velocity. Okay? But look at the incredible relationship between these two. Okay? This is called cultural intersectionality. Okay? Between the French and the Irish. Okay? So what do we got here? Okay, notice that the slope, that's this thing right here, the slope, the V slope, is P over there. Here it's 1.6. Okay? That the V slope, this thing is 1.6. You can see that it's 1 out and down here to 0.6. So there's 1.6 in distance right there. And then there's this, and it's got a positive slope, plus. All right? So there's that 1.6, there's the 1. Again, this is all nice graph paper that lets you do that. Okay? So the connection is that the V slope intercept, this where this guy meets right here, is minus 0.6, 0.2, 0.4, 0.6. Okay, down, minus. Okay, the V slope intercept is equal to the Hamiltonian at the corresponding point. Okay, the corresponding Hamiltonian at this point is 0.6, matches the intercept except for a minus sign. But then the reverse term, the P slope intercept, that's this P slope of the line right there, is minus 1.0. Okay, and that P slope intercept is the value of the Lagrangian. That's this value right there. Okay? The value of the Lagrangian. Let's see if I've got that right. The Lagrangian L of V, that's this distance right here, is minus the p-slope intercept, which is minus a minus is plus 1. Okay? So I've carefully drawn arrows between very different geometrical concepts that are equal in number from Irish to French way of doing things. So once again, here the actual velocity, which the Lagrangian is a function of, it's equal to the p-slope. That's the first equation of Lagrange. Okay? Take it back. That's the first equation of Hamilton. And then this one is the first equation. The v-slope is the momentum. Okay, so this slope of 1.6 is the momentum value. Okay? That's a lot to sort of swallow at once, but that is the situation in classical mechanics. Okay? Let me go ahead and make sure it's on this screen as well. Okay? Now, I'd like to show you something. It's way ahead. It's Unit 8. But this is where it comes from. This is where, in just using the waves in one axiom, the speed of light is constant. Speed of light is a 45-degree line on this scale here. And we're talking about energy versus per space. That's per time. Energy is frequency. Per space, inverse space, is momentum. How many wrinkles do you have in time? How many wrinkles do you have in space? That's what waves deal with, and that's what quantum waves deal with. So, what I'd like you to just see for a brief moment here, and if you're really interested, you go for it right now, but this is what is available to you if we're on the web. And all you have to do is move the mouse to make the thing bigger. And then you can go and you grab one of these circles and try different values. I mean, you can start off right here where you can't see anything. But as you go, you make the momentum bigger. I'm pointing the arrow right there at the end of the momentum line, the P line, if you will. And I am making the Hamiltonian, this is the relativistic Hamiltonian, exact for, well, what? For a box of light that has this much mass. This is mc squared from there to there. And then this is the dispersion curve for a wave in a waveguide. If you've been studying electromagnetism a little bit, you know that's thick. Meanwhile, this thing is the Hamiltonian function of momentum. That's the Irish. The French is in this little circle. You know how the French are so urbane? You know, they live in nice villages, right? And they kind of make fun of the people that are out in the country, okay? This is the Lagrangian right here at that particular setting. And this is the group velocity. That's the classical velocity of this funny relativistic thing. And it never can exceed c. So this is where the high energy physicists live. They live with Lagrangians because Lagrangians are nice and small. Meanwhile, the Hamiltonian is out of here. The Hamiltonian has no limit. It just goes to infinity. So we, in this laboratory, we're all within a pixel of this point right here. Very seldom do we have any energy that's anywhere near the size of the rest mass of whatever it is we're working with. So you're stuck in, you know, as long as you stay with us and don't go over to work at the collider or someplace. And if you work at the collider, you're down here, you know, crunched down into there. Okay? So this is where that idea of those two equations is just a result of what waves do. And what you've got here is a slope, that's this blue line, okay, whose intercept sits right next to the Lagrangian. And the Lagrangian has a slope, and the Lagrangian is nothing but a circle. The Lagrangian is sitting right here with its slope coming up and contacting the axis, and intercepting the axis at the Hamiltonian. Now you're amongst very few people in the world that have seen this structure. Are you happy about that? Or are you, mad? I don't think this could possibly be right. It is. It is. It exists. Okay. And when you play with this thing, you can turn on everything if you want to. There's all ways to approach this. Let's just turn everything on so that you see what is in there is a space-time graph. Actually, it's the per space, per time graph. And it is doing the usual Minkowski thing that happens where you make a space-time graph of something that's going, well, it'll tell you up here what your v over c is. That's about 0.6 the speed of light right there. Okay? Well, this is something worth thinking about. This is the way you can get your mind around what we call modern physics. And it goes back to Thales, 600 BCE. No geometry in there that you can't, that Thales would be surprised by. He just wouldn't know what the hell you're talking about when it comes to physics. That took a lot longer for us to discover. Okay, so here's just a sketch without going to high speeds. There's what it looks like for any speed. Now, let's go back to this, because this isn't a quantum mechanics class, and I'm going to just back out of it for right now and take on the things that this being the main point, all you need to say is all colors go the same speed. All of this geometry falls out. This is a really simple axiom. All the momentum conservation, all the energy structure, everything falls out. So I consider that a logical success when we can get something so complicated that it requires graduate school to learn, reduced to really beautiful way to learn about the hyperbolic functions or the circular functions. Use either one. There's a thing called the stellar aberration angle. That's the polar angle of the Lagrangian. It's all child's play when you do it this way. And that's the way physics should be. If you're really making success, you try to make it. So this, on the other hand, is a little bit challenging. So let's put away the thing that makes sense and get something up here that doesn't make quite as much sense, at least not unless you look at it carefully. So here's where we're going to figure out what it really means to have no explicit dependence on a velocity in a Hamiltonian. Then we'll play the same trick on the Lagrangian. Okay? Using that cross-section that I had there, forgetting about the fact that there's an MC squared thing that has to be added to all of this stuff that is the fundamental heartbeat of all matter. But we'll just go ahead and pretend that we can get away with our work putting the energy at any point. And you know that's kind of true, because nothing that you measure depends on the energy value. It's always the difference or derivative of that energy that you measure. You can put your zero anywhere you want until you get into the relativity and say, oh, I got to put it at MC squared. Then it nails you. But for this class, put your energy origin anywhere you want. Okay? Differences don't really matter. Okay, so what do we got here? What I've got is a bunch of secant lines. That's L as a function of V, is equal to P dot V minus something called H. Well, here's H. It's an intercept, okay? And I'm just playing around with the intercept now. I'm trying certain values. V of minus 2 gives me an intercept, you know, right there. Okay, V of minus 1 gives me an intercept right there. And so forth, okay? Until finally, I'm off the curve. The tangent doesn't touch the curve anymore, right? So I back up. That's the point I'm interested in right there. That's where the tangent line points to the extreme value of h on this axis. And at that point, the derivative of the Hamiltonian with respect to velocity is 0. So there's the functional picture for just a classical way to approach this subject, giving us what we have been assuming, sort of, as we go here. Okay? So the contact point that has the maximum h, this is an extremum problem, and at that point, the partial derivative of h with respect to v, or if we only had the variable shown, the derivative with respect to v is absolutely 0. You know, that's the way you find maximum and minimum, extreme values, right? Set the derivative to 0. Well, here's a pretty fancy version of that idea. Okay? Now, the next one on the list here, you see, this is really stating what it is I'm after here to make this, or let's do this one. Okay? Well, you know, it's the same story. The same story is going to come up on there. So, it's rephrasing it at the very bottom of this thing here. This zero derivative at each point, v, of the Lagrangian, where your slope varies, okay, but varies from point to point. When you're on a particular point, okay, this Hamiltonian has no variability, unless I cheat and make 2 points, and that's not what we're doing. Okay, so here's the Lagrangian story. Okay, same deal. Okay, secant lines on the Irish curve, the Hamiltonian curve, function of momentum. Okay, and the intercepts are L, and it's reaching an extremum. Okay, and at that point, we've got this situation. That's how you get this partial derivative of L of P is equal to 0. I haven't seen this anywhere except the slight approach to this in Arnold's book. Arnold is a famous Russian. The Russians are way ahead of the Americans on mechanics. They were the ones that brought us the analysis of chaos. Kolmogorov, Arnold, Moser. The KAM theorem of classical chaos is legendary, and that was all being worked out in the late 70s, 80s, 90s. Okay. But except for Arnaud's book, he didn't go into this detail. He really just kind of drew a funny sketch and then stopped. So, one of those things that we're getting in this room that you don't find outside of this room that much. Okay, now I'd like to take a quick analogy here, just for the sake of if you're taking thermodynamics or statistical mechanics with thermodynamics, you've probably seen where you take the internal energy, and that has to be is written on a gold tablet somewhere. That particular internal energy, as most people do it, is a function of entropy, S, and volume V. And this is a two-dimensional, very simple thermodynamic system. But I make an analogy here with our velocity versus momentum. A new function called enthalpy has a different thing. It has a letter H, first of all, here. That's what enthalpy is usually designated by. And it is still a function of entropy, but now it's pressure. Okay, so here we got these two different situations that are analogous to the Lagrangian and Hamiltonian differing in their kinetic variable, the velocity in one case and the momentum in the other case. So, what do you get? There is a thing called the Legendre Transformative. Legendre was doing more than just mechanics, and that's French school again. Here he writes, and he writes the enthalpy as a product of pressure and volume, those two variables that we're trying to switch, and the internal energy. Okay? So this is very much like our Poincare relation, except for a minus sign there. And he gets a new variable here. The pressure is minus the partial derivative of u with respect to v. And there's that little s subscript that you would find in a lot of thermodynamics saying, don't move that variable. It's only partial with respect to v. Okay? So, that's what I'm trying to show here. Now, just put in different names here. Let this be the Lagrangian of a position and velocity, and it's kind of nice that the v of volume is just the capital of the velocity variable here, okay, is defined as a function of entropy, well, position r and volume v, okay, and then we get this Hamiltonian is analogous to enthalpy, which depends still on entropy. That means still on position r, but we're changing v to p. Okay? And there's the relationship right there. And this is the pressure, this is the equation, with a minus sign. So you see the difference here is that we've got a minus, and that makes sense for us to have that. And you can see that maybe in the geometry that was there, but I didn't go into that. But here we got a plus sign. So there's an example of these things. So except for the plus and minus signs, our Hamiltonian going from Lagrangian, in other words, if you know the Lagrangian, this is how you get the Hamiltonian, and you do it all the time, no matter how many variables you have. This is really a golden relation, and we'll see why it is. It's because of the underlying phase of quantum mechanics that makes classical mechanics work, ultimately. We've got this momentum here that we were talking about. Okay, these are things I'm putting up here to help you with other subjects, but mechanics, we really need this stuff. We need to understand it as clearly and solidly as possible. Okay? Now, the whole idea of a contact transformation is also a deep one. Then we're going to go back to sophomore physics today. Okay, so the remaining 30 to 40 minutes of the class will be a relief. Quite unlike the last lecture where it was just the opposite. Okay, so first I want to show you what this looks like in general. And then I want to show you a sophomore physics problem that uses this. So, to get ready for that, I'm going to go ahead and put this screen ahead as well to about where we are. In fact, I might just take it right over the edge. That's what we're looking at in general, is a general contact transformation. Now this started out, I think, in the olden times. Okay, we're talking before you had graph paper and all that kind of stuff. But the ability to draw curves, this is a neat way to do it if you can pull it off. And the idea is, you've got a curve here in the variables y and x lowercase. And we've got a contact transformation generator function. This is going to be called our action function in our mechanics. And I'm using the letter S, which is very often used to label action. And action turns into quantum phase when you make the connection. So we're getting here at something that is what waves do, perhaps first of all in your physics knowledge. Huygens principle is a really good example of that. We have a bunch of emitters that are making spherical waves, right? And each spherical wave goes out and has an extrema. That extrema is called a cusp, or there's another name for it, I can't think of it right now. Bonk, bonk, bonk. I'll think of it later. But anyway, that's the wave front created. by all the little wavelets. Okay? That's what this is, except it's just a mathematical structure here. I give you a function of both variables, set it to a constant, okay? And then, each time I have a point here, I then go over here and plot all the possibilities for that. This function right here. I look at this function, I'm actually looking at this one, I look at that and say it was a constant, so it's 10 in each of these cases, okay? I look at this thing, I know what this value is, so I simply plot S of big X and big Y in the big X, big Y graph paper. Okay? So I go like that. Okay? Well, that doesn't help you much. That says that this point maps to all of these points. Doesn't help me much, does it? Then I go on to the next one. Okay, this point right here. I look at this equation for x1, y1, which is right here. Well, it does the same thing. This thing equal to 10, the big X and big Y lies on that curve right there. Okay? And then I do it one more time, say up here. Same thing now, except that it's x2, y2, little x2, y2, giving me all of these points. Then I say, I don't give a crap about all these points. I like this little thing that's forming right here, the wavefront. That's the contact transformation curve of this curve. And that, you can see why it's called the contact transformation. It's because it's all the contact points. That's the general case. Okay? Now what we just discussed was a Legendre transformation. Was this one. It's a contact transformation where all of the contactors are straight lines. That's a pretty special case of this. Okay? Then it gives us the equations that we have. H equal q dot p minus L. Remember, q dot is the velocity in the notation that we're going to be using fairly shortly. If we get out of this elementary review unit. But that is the geometry. Now, if in fact I take this curve and go dip, line, dip, line, dip, line, you can see how having a bunch of lines, and you wouldn't draw the whole line, you just draw little segments of it, would really be a powerful way to get a precise mapping curve. Better than what we've been doing where we get a point. Here you get a whole line and the point. Okay, so that it's an artistic graphics ruse. It's a tool used by people that had to be really careful about drawing lines on a plate that was going to be used to print. You see. In thermodynamics, that's what they did. They make brass plates with all the important curves for a particular steam engine or something like that. Okay, so this has a big history, this contact business, but mainly has a wave history. So that's the thing. And if you can go this way, you can go vice versa. There's got to be a bunch of those guys to make this curve from that one. That's interesting. How's the inverse contact transformation work? Okay? So these are all things that we're going to wrestle with a little bit later on in this course. Okay? And these are not things that you would throw at sophomore physics, guys. But you should. You should throw it at them. And that's what I'm going to show you here. Now, let's just say one more thing about this before we go back to sophomore physics. The differential Ldt. Okay? And I'm putting a dt on there and on there as well. So I'm just taking the Poincare relationship, L equal P momentum dot velocity, Q dot here, not V, minus H. Okay? And looking at it. Okay? Well, what that wave thing I was waving my hands up, in front of, the momentum is h bar k. That's the de Broglie relation. It comes in 1929. Actually, it was a little earlier than that. It was like 22. But it was 1900 when Planck said E equal h bar omega. Actually, he said n h bar omega, and that's a big difference. But that is your phase. you see. That's quantum phase. That's why the LDT is so key. Now I write H up there outside, but this is what you would be doing. So that's the quantum phase differential that you're looking at, and we'll make a fuss about that, as I say, later. This is quite an extraordinary plane. It needs extraordinary proof. So we're going to be playing with this in Chapter 12 of this review unit, but Unit 8 is where it really takes off. Okay. Well, I'm not going to ask any questions, because you should have a lot. But I'm going to take you now to a contact transformation that really deals with something that we see when we look real closely at the National Institute of Standards and Technology, the thing that generates accurate time, which reads into this nice wristwatch I bought at Walmart yesterday to replace a piece of crap I had before. In any case, what it is a bunch of cesium atoms that are sort of allowed to expand. It's a little tricky way to get them expanding as they're being thrown up into this vacuum chamber. Okay. And the idea is to have a bunch of atoms that are stationary, which you can optically read the cesium frequencies, which is our time standard that exists, you know, for commercial use. We have that lab has much better time standards, but this is an interesting one. Or it's just a fountain. This is what we're really looking at here. Is boom, and it makes an envelope, a contact envelope. Okay, and that's what we want to calculate. The shape of the volcanic plumes on Io. So here's a small example of this. This is a little bigger. Okay? And there's the plume. Okay, and there's another one on there. And there are a lot better ones that have been shown since these pictures were taken. But we're going to make our own simulation. And then I'm going to have you do some problems that involve this. Okay? Okay. That's the simulation right there. We'll look at that in a minute here. Let me put the stationary object up on this screen right there. What we're going to be interested in is the algebra for just to get started here. Then we'll come back to the geometry. So I'm going to put that part up here. But in the middle of the screen, I will go ahead and let this thing, I hope, run an animation. And let's see if I can get it started here. This is, I'm trying to think, what is the name of the app?
Cool it.
Okay, this is Cool It. Yeah, right here. Okay. When I first did these things on System 9 of the Mac, and it was actually System 4 when I started this stuff, everything was based on an interface that's called Face It. And so I named all of the things it. Cool It, Bang It, Whack It, I mean, you name it, Quant It, they're all something it. So, you know, that's a little gross, but it's still good. There's the explosion, okay, from a point. And now the top is just reaching the highest place it can go, and there's a contact point that's on either side slithering down the parabolic envelope of all those little parabolas. And this is being done in uniform gravity. Okay? So, for what it's worth, that is the animation, simulation of that sketch over there, which came off of, that was probably System 6, with all the pixels showing. So we're going to quite often in this class do what most mechanics classes don't do, is do the mathematics of the family of curves, the whole family of curves that have contact envelopes, and understand the geometry of that. Okay. Because that geometry is pretty much what you get if this was a quantum simulation, except that in here there'd be all sorts of waves, and then there'd be an exponential fall off right at the contacted envelope. We've done a little bit of that, but not much. Okay, so excuse me. How does this work? Well, first of all, you go to UP1, which guys are, some of you are labbing and teaching and whatever, and get out your equations for a trajectory, one trajectory, as a function of the elevation angle and the velocity initial, whatever velocity the cannon had here. Other than that, it's uniform gravity, nothing fancy. We'll do the case where it's actually a spherical Coulomb problem, but and we'll do the inside the Earth examples of trajectories like this. But for now, it's UP1. So you've got the x and the Vx, and then you've got the y and the Vy at time equals 0. This is what it would be as the time goes, given the initial velocity right here. That will be integrating this to a time linear, something linear in time. Okay, the velocity will be linear in time, starting out with a high positive value and dropping to a finally very large negative value. Meanwhile, this will be happening also. But one of the ways you can analyze what happens here is just imagine what it would be like if you were to get into the reference frame of what's going on here. If you did, you'd be riding up, always at the center of the circle until the circle reached the top there. The center of the circle, you can see, that's its turnaround point. And then it starts dropping. That's you riding in a space capsule or something, always seeing an expanding sphere. That's all you ever see. And that's this sphere right here. Okay? So that sphere is also contacting this envelope. And that's you got to get all this stuff in your head before you understand what this geometry is really doing. Okay. In any case, taking these two guys together and eliminating time gives you an equation for y of x as a function of x. That's a really big luxury for problems like this, to have that function. But that's usually the hardest part of it, is to get a function like that set up. Now, I'm going to jump ahead here one step, and also over here, so you see it from both sides of the room. Very important part. I'm taking this luxury and making immediately my generating function. Okay? So I'm going to say S of the velocity parameter, the initial velocity parameter, the initial angle parameter, colon, and then it's a function of x and y. That's all we care about. We don't care about time anymore. Trying to figure out what's going on in space. And S equals 0 is the equation that this is. Okay, so this is, that particular generator equals 0. All right, so that is a contact transformation S of velocity 0 alpha as alpha this way. I got 45 degrees, I got 60 degrees, I got 75 degrees. I'm varying here without changing the velocity. So we're assuming that the objects have the same velocity. Now in the case of the rising cesium circle or sphere, that's a pretty good approximation, that they all came out with a particular velocity that was arranged. On the moons of Io, it's an approximation, an idealization. We're picking an average when we do that. Okay, so EOS is kind of a fuzzy thing. It's not got something that looks like that. But in any case, here's what we're looking at. We're looking for contact points, right? Or an equation for all of the contact points. That's, you know, that's the job of this particular homework problem. Okay? So it's the envelopes that extreme contact points with each trajectory. And each one of those is at a point where varying the alpha doesn't make much difference. As I vary the alpha, I get a lot of change here, here, not so much here, and then I get a lot of change down here by varying alpha. I get the range to change a lot, right? But nothing changes right here at the first order. That's the key to finding contact points, is looking for that stationary behavior. Partial of S with respect to alpha, 0. I got to solve that to get the envelope. Okay? Now, just out of curiosity, how many people have solved problems like this in a calculus or whatever mathematics course? Just out of curiosity, anybody? I mean, 20 years ago, all hands. Not anymore. You guys are being cheated. Not here. We're trying to make up for that. This is not an easy derivative. This is a sophomore problem, but this thing gets to be a mess. Not a terrible mess, but much less nice than some things. I go through and I cancel a few things from that partial derivative, and I get that. But I'm still not home. I've got to feed that back into this thing to get the y envelope. But I do finally end up with a really nice result. Well, sort of nice. I got an x here. Okay, I got an x squared here, but I got to cancel it there. I'm still not done. It really does get a lot simpler here. That's what you get. It's a parabola. You kind of guessed that, didn't you? Okay, but it's nice to see it. These extremal problems, these Feynman path techniques, that's really what it is. Feynman wrote his thesis, terrible thesis, under Wheeler, and Wheeler let him get away with it. But then he hooked up with Alfred Hibbs, and Hibbs said, hey, what's this piece of crap you have to write? But this is really neat, let's write a book. And the Feynman path integrals then became something that you really use for certain rather neat applications. In any case, this is a nice problem to look at. And there's a couple of examples there that are shown. And this is from Galileo, must be, and anyway, you can click on all of these and get more pictures than ones I've pasted up here. This is not NASA at its best. Coming off the NASA site here. These guys need a geometry lesson. That looks more like a fountain in Las Vegas than the actual parabolic things that you get on moons that have volcanoes. Now the thing that is going to come up here is, in order to analyze all of the pieces of that, this kite geometry really helps. So that's something, when you do this problem, please avail yourself of that. But these are basic questions that you ask about this bunch of particles. Say I have here 1, 2, 3, 4, 5, 6 different things, and I get 6 times 4 is 24 different orbits that are all going to make that kind of envelope. Okay, and it's a good idea to see if you can answer the simple questions like this. Where is the blast wave? That is, where is the circle? Where is the circle of red dots at each moment? And where is it touching the envelope? That can give you a clue where the envelope is. But in particular, we'd like to know, if we're talking about the single parabolic trajectory, you'd like to know where the focus of that is, and then you'd like to know where's the focus of the envelope. presuming it's a conic section at all. It kind of looks like a parabola, and we already calculated algebraically it was, so yeah, that makes sense. And question 3 here, how high can alpha equal 45? 45 has the biggest range, but how high does it get? It does often go somewhere there. These are all questions that we look at. Now, where is the focus for this particular path? Alpha equal 90 degrees. That's pretty easy. The alpha equal 90 degrees goes boom. Where's focus? Anybody have an idea of where that focus is? Where about would be the focus of this, say, 89 degrees or 91 degrees, which, let's just for the sake of argument, goes up about there. That's the way to think about the problem, right? What if it's a little off of 90? Where's the focus? And remember, I told you the focus is where the parabola slants at 45 degrees, right? And remember why that has to be, because there's a light ray coming up the axis, the parabola has to go through the focus, right? Or stated another way, light from the focus has to bounce off the parabola and go directly out on the axis. So it has to be 45, right? But what about the one that goes straight up? See, it's these limits that get a little confusing, right? So let's blow it up. Let's suppose that I blew that thing up and I got a parabola, you know, was like this. Where's the focus? So down here, down here. So that's where you got to think, right? Where is it opposite the 45-degree slope? And it's a really skinny parabola, right? It has to be really close to the top, right? And if it's straight up, it has to be at the tippy top, right? You can almost see that no parabola in there, right? 45 degrees, 1 pixel off the top. Okay, this is the kind of thinking you got to get good at. Just manipulating algebra, that's crap. That can't go far. You got to think things through. This is where the fun is. Okay. Where's blast wave? We're talking alpha equal 90 degrees, but we're talking about it. It's on the blast wave of some kind. Okay. Well, it's just wherever something blown with this particular velocity v would be at the maximum. That's a sophomore physics problem right there, if there is one. And so forth. These questions get harder and harder as we move along here, asking about things. Okay. Just using the algebraic equations, you can answer a lot of these questions, but thinking them first is good. Where's the kite for this particular 45-degree thing? Where's the maximum range, right? Well, if we discover that the maximum height of 45 is there, it's going to be twice the range. But basically the idea is this thing comes off here at 45, that's got to be the tippy top, and that's got to be the place where it's 45 degrees, just like this was 45 degrees. Focus has to be right there. Right? All kinds of questions you can ask about these simulations, you see. And if that's a contact point, then there's a sphere contacting that thing, and that means that this is on the envelope right here. Because remember that the sphere is what I call the blast circle is touching the envelope at that particular time, sliding down the outside. Let's go ahead and run this again, just to see that. We'll let it run with the original thing. There's the touch point for this particular one. and then it's slither on either side as you go down. And there would be the thing slithering by the x-axis, just passing right now. And all the rest of them are going to be inside of the extended parabola before long. Okay, so there's a picture of, kind of a picture of that particular situation. Envelope, contact points, all that stuff. And this is what's really cool, we're going to see this over and over again, is the envelope contact point and the envelope focus must line up. That is, here's the focus of this parabola, it has to line up with the envelope focus. There's the envelope parabola sketched in there. And that's for the square kite. Pick some other angle. I think this one shows it pretty clearly. That may be the last. Let's see if I've got, yeah, that's where the lecture ends. You can see the ending point there. But here is a kite that goes with the directrix for the envelope. And then inside that is a mini kite that goes for a directrix for this particular point. That's kind of neat. And answers a lot of questions that are on the side here. So I'm going to give a problem similar to this one for you to chew on come Wednesday. Okay? And then we're going to do it for inside the Earth. Imagine a neutron starlet. It goes along and goes through a patch of uranium. Now, the reason we don't have a neutron starlet is pretty obvious from nuclear physics. And neutrons by themselves, and particularly a pile of them, with beta decay, boom, electron, neutrino, and a proton coming out of it. Okay? That would be spectacular. Okay? But we can imagine. We can imagine that a neutron starlet would hold together until it went through a patch of uranium and then it blew up. Okay? What kind of surface do you make inside the Earth? All those little tiny fragments of the neutron star. So that's something we'll tackle before too long. Okay. All right. Any questions? It's a quiet class. You've got to learn to take advantage of it. Try to make the professor look stupid. That's your job. For me, it's easy. Well, I'll say maybe not all the time, but some of the time. Okay, we'll see you on Wednesday.